I'm Andrea. I'm the Vice President of Engineering at Veridice. And in today's talk, I will present Picus, our automated verification tool of zero-knowledge proof circuits. All right, so in the last couple of years, we witnessed an emergence of ZK solutions, right? So now we have privacy-based contracts, rollups, privacy-preserving blockchains, and many more. And actually at Veridice, we audited several of these tools and services, and we actually realized that sometimes the manual audits can have their challenges, so we wanted to push the boundaries of ZK security, and we implemented automated tools that can detect bugs and vulnerabilities in ZK circuits. And Picus, the tool I mentioned before, is one of them. All right, so before diving deep into the internals of this tool, I would like to talk about the workflow of a zero-knowledge proof circuit. And for this example, we chose to talk about Circum. All right, so in general, the workflow of a zero-knowledge proof circuit looks like this. So we start with the source code, which can be written in DSLs such as Circum and Hello2, and then this source code is transformed into two entities, which in this case are the witness generator and a set of polynomial field equations. And the latter is afterwards used to produce a prover and a verifier that are integrated with the ZK applications, and these two entities are collectively called a snark. All right, so one thing that I wanted to mention before moving forward is that unlike traditional programming, the source code contains both the computation and the constraints, and this is, a huge difference or a shift of paradigm. All right, as I said, we will focus on some Circum examples. So this is a very simple example of a ZK circuit. So you'll see in the last part of this code snippet some assignments, right, for the output signals and some equality constraints, right? So these operators are actually used to generate those two entities, right? So for the assignments, we have the computation part, which assigns these computations to the output signals, and the constraints, which are then used by the verifier to verify that the proofs sent by the prover are indeed, correct. All right, so this is the workflow. Basically, what the users do is to provide the inputs, then these inputs are encoded into a witness that is afterwards generating the proof, and the constraints are verifying that proof and output, okay, this proof looks correct, and no otherwise. And our goal here is that, we have to somehow create our circuits to maintain this property, basically. So the computation part and the constraint should be equivalent. Why, we'll see later, but the main idea behind this is that if these two entities are not equivalent, then our constraints could accept invalid, proofs, which is bad. All right, so let's have a look at this equivalence property. So this is the way we formally express this property. So basically, for every x, which is an input of the witness generator, then the output of this witness generator is has to satisfy the constraints, right? So you can read this property this way, like every input-output pair of P must satisfy C, the constraint, the set of constraints, and every XY pair which satisfy C must be an input-output pair of P. So there is equivalence between these two entities. All right, so we've noticed, like during audits and based on the attacks that happened in the industry in the past, that this property is very often violated. And we will see that this is like this lack of equivalence between these two entities actually is the source of this class of bugs, namely the unconstrained circuits. All right. So these unconstrained circuits are super related to the notion of non-determinism. So basically, for a given input x, we can, verify that multiple distinct proofs are valid, which is not desired, right? So this, in other words, this means that the verifier could basically accept invalid computations. All right, so here are some examples of the hacks that happened in the past. Here we could mention like Tornado Cache. And now let's just have a look at an example, again, in the Circum DSL, right? So this is an intentionally buggy snippet of code. What you see in red is where the bug is located. And basically what happens in here is that we don't loop up to n, we loop up until n-1, and this is the cause of some unconstrained circuits, output signals basically, and this results in the possibility of an attacker to pass any value for this output 2. So if we instantiate this snippet of code for an n equal to 3, then we have like this vulnerability uncovered. All right, so how are people usually testing or trying to find these unconstrained bugs in their zero-knowledge circuits? So there are two main techniques, namely static analysis of the constraints and SMT solvers. So for this analysis, static analysis of the constraints, things like look this way. Basically, you have like you have your circuit, you have your input, output, and assignment, and you can reason about the way the code looks like, right? So in this particular case, since z is a function of x and y is a function of both x and z, it means that we can infer, like based on this structure of the code, that y is uniquely determined by input x. So in this case, we have like a constrained output signal, right? So everything looks clear. But we have another, more expensive technique, which is using SMT solvers. So basically, what you see in there is a logical formula that encodes that non-determinism behavior we saw on the previous slide. So basically, if this formula is satisfied, it means that we found an unconstrained vulnerability in our circuit. Of course, like there are pros and cons for each of these techniques. Static analysis is in general more scalable, right? But it is not that precise. Basically, it produces many false positives. So the users, not the users, like the developers have to, check those false positives and in the end, verify if they make sense or not, right? The SMTs are more precise, but they don't scale as well as the static analysis, right? So what we did at Veridice was to basically combine these two techniques into a tool called Picus. So Picus is a verifier that automatically checks if a zero-knowledge proof circuit is under constraint. It takes in the circuit, namely the constraints, and it outputs if the circuit is deterministic. Like that green tick means that the circuit is deterministic. The output can be the circuit is under constraint or unknown. And in the case Picus outputs unknown, it means that it reached that timeout we provided it with, because the users have to provide the timeout for the process, the analysis, right? It cannot like run forever. All right, so How does Picus looks under the hood? Basically, there is an interactive loop between the SMT part and the static analysis part of it. So there is this sort of shared knowledge between them. So for instance, when the SMT gets stuck, it can use some input, some help. It can use some help from the static analysis, and the loop continues to run. So I mentioned before that this tool of ours combines the strength of the static analysis and SMTs, and these two instances interact in a loop, and the partial result could be used in this interactive loop to make progress, right? All right, so if you want to check how our Picus tool works, you can access our GitHub page. Also, you can scan this code and read our PLDI paper where we present the result and the technique behind Picus. So I'll just give you a few seconds if you want to scan the QR code. If not, you can approach me after this talk and I will provide you with a link to the paper. All right, so I recorded a demo of this Picus tool, and basically we will use the same example, like the one with the for loop, right? And I recorded two demos of Picus, basically when we input the example which is buggy and the example which is fixed, correct? All right, so here you can see our security as a service tool. This is the interface. Oh. It is not starting for some reason. Could someone click on the slide, maybe? It is a video embedded in the presentation, so I'm clicking on this, so it is not doing anything. Oh, but I sent a PPT. All right. It seems that this presentation was converted into a PDF, so we cannot play the video. Anyway, so yeah, our Picus tool was tested on a few benchmarks, and we gathered some information from some circuits from the circumlib, and which consists of 163 circuits, and of course, we also gathered some examples from the circumlib utils and circumlib core, which coverages 50 of the most security critical template in Circum. All right, so these are some statistics, some data about the number of circuits that we tested and the number of constraints that they contain. Right, so here are some results. Picus was able to verify 101 circuits out of the total number of circuits, and it proved that those were properly constrained, and it also found that 8 of those circuits were actually under-constrained, and we reported those vulnerabilities to the developers, so fixes are on their way. So a few takeaways. Picus is a fully automated tool that is able to verify and find under-constrained bugs in zero-knowledge circuits. It also leverages static analysis and SMT reasoning. And this work was a collaboration between 0xSpark and ZConduit. So this is a good moment to thank them for this collaboration. All right, so thank you very much for attending this talk. If you are interested to actually see the demos of these tools, we invite you to join our workshop on the ZK tools. We also present a static analyzer called ZK Vanguard, besides Picus, and if you are interested to check some of our audits that we performed in the past, please scan that code. We worked with many of the leads in the ZK area. Thank you.